Hello everyone, welcome to this interesting video on general form of conic section. So in the last video we have discussed about the general conic equation which has been given by R is going to be equal to okay L divided by 1 plus or minus E cos theta. So this is the general form of a conic equation. Okay, so basic conic equation also we can tell. So now today we are going to see how to identify a conic section. Okay, if some general form is being given in a Cartesian coordinates, let's say x and y. Okay, maybe in a two-dimensional stuff. Okay, so three-dimensional also we can do it, but it's a bit complicated, so we'll just omit uh, at present moment. So we'll go with the two-dimensional stuff. Now for any basic conic equation we always represent the equation like this. We have ax square plus by square plus cx plus dy, okay, plus exy plus f is going to be 0. So at present we don't know whether this equation represents a circle equation, ellipse equation, parabola, or even hyperbola. Okay, so it is actually we cannot predict it currently by seeing itself. Okay, but what we do is like we have set of tests that we need to perform whether to identify this is circle, ellipse, parabola, or hyperbola. Okay, there are some conditions whether we need to identify what type of orbital profile whether this equation corresponds to. Okay, so for doing that we need to have some conditions. Now let's say if this is to satisfy for a circle section or a circular orbit, then probably we go with the circle. For circle section we have some conditions. If A is going to be equal to B and your E is going to be 0, then probably this equation represents a circular platform. Okay. Now it is going to be a parabola. If it is a parabola, then probably you need to only consider A, B, and E here, nothing else. Okay. So you multiply AB, okay, and we have E by 2, you take E by 2, okay, and you deduct AB minus of E by 2 whole square you put, okay. If this is going to be 0, then probably this is going to be a parabola, okay. Now go with the ellipse test. So if this equation corresponds to ellipse, then it has to obey this condition, AB minus of E by 2 whole square greater than 0, okay. And if it is a hyperbola, you go with hyperbola, and here it is going to be again AB, you minus E by 2 whole square, and whether this is going to be less than 0, then you can fix it, this is going to be hyperbola. So these are the some of the tests we need to perform. Now to understand this much more clear, let's say an astronomer found out an equation of a second order degree equation in the Cartesian form like this, but he is not able to predict whether what type of a profile that this is going to exhibit. So we are going to deal with that now. So we have 2x square plus 3y square plus 6x plus 7y plus 8xy plus 100 is going to be my, let's say we have a numerical exercise over here. So this is actually an equation which is being found out by an astronomer, let's say. Okay, an astronomer doesn't know what is the uh, conic profile or an orbital profile this particular system is exhibiting. Okay, so I think we can find out that. So now let's say you have this question, so I'll write the question: 2x square plus 3y square plus 6x plus 7y plus 8xy plus 100 is going to be my question. Now I write the general form of the conic: ax square plus by square plus cx plus dy plus exy plus f is going to be 0. Now in order to deal this in a systematic way, okay, only thing you have to remember your A, B, C, D, E, okay. So you just draw a small table or something and you mark A, B, C, D, and up to E. E is my exit, okay? So we stop up to the exit. So we have up to E. Now just draw a table like this, okay? And just start filling the A values. You have 2 here, you have 3 here. Just keep filling 6 up to 7 and up to 8. You stop here, okay? Now this is ready. So this is ready actually. Now let's go with the sequence of test. So if A is going to be equal to B, then probably you're going to get a circle. So it is not passing because A is not equal to B, and we also have an E term which is not 0, that is 8. Now go with the next condition. Now let's say in order to go with the next condition, you only have to do A and B. Okay, now let's say your A into B is 6 here. Okay, now you deduct. Okay, what is E here? E is going to be 8. The half of 8 is 4. You square the term, 4 square. Okay, now this is going to be 6 minus of 16 is going to be a minus 10. That means this is less than 0. That means which condition is satisfying? This is satisfying nothing but your hyperbolic equation. That means this equation corresponds to a spacecraft who is trying to escape from the planet's gravitational pull. Okay, in that condition, your spacecraft will be exhibiting a hyperbolic profile. Okay, so that is a condition. If your spacecraft is trying to escape, now let's say this is a planet. Okay, now you have a spacecraft. Now it has to move on to the next orbit. Now you fire some rocket or something. Okay, now with the help of the firing, so it is able to achieve this position. So this path followed by the spacecraft is called the hyperbolic profile. Okay, especially for performing a high escape velocity. Okay, in order to jump, in order to escape from the gravitational pull. Okay, so this is going to be your hyperbolic profile. So let's say we have different equations, and accordingly you can try to find out what type of profile it is going to exhibit. So for this curve, you always have your eccentricity value. Okay, your eccentricity value is always greater than 1. So this is going to represent me a hyperbolic profile. Okay, this is going to represent a hyperbolic profile where eccentricity E is going to be greater than 1. Okay, that means here this can be a combination of your escape speed. A spacecraft is trying to implement a higher escape speed, so that is the reason this profile is executing a hyperbolic profile. Okay, so this is a classic example how to determine whether any orbital profile is a hyperbola or parabola or even a ellipse or circle. So this is a practical application of this equation. Okay, so that now the astronomer is very happy. Now he is telling, okay, I found out this is basically a profile of a spacecraft who is trying to escape from a planet's gravitational pull. Okay, so that is why we have received this equation, which corresponds to your eccentricity value is greater than 1, and it is also obeying this standard condition. Okay, now this also you have to keep in mind whenever you perform any orbital analysis. So this will help you a lot. I hope this short video is informative for you, and you can try practicing out with different conic equations, and you go for a test for circle, parabola, ellipse, and hyperbola, and accordingly you can perform your analysis. So always remember, if at all you have if you are getting a circular orbits, okay, if at all you are having a circular orbit, it can be an Earth satellite combination. Okay, so these orbits are mainly exhibited by low Earth orbits, maybe from 1000 or 150 kilometers to maybe 1500. Okay, roughly I'm saying it can be even higher. Okay, or maybe 2000 itself. So roughly from 150 to 1500 kilometers where satellite is being placed, and satellite will be revolving around the Earth in a circular path. Okay, So that is where your circular orbits will come into picture. And if it is an ellipse, as you know, your sun and the planet combination. So that is going to be your ellipse. If it is a parabola or hyperbola, you can fix it. Your spacecraft is trying to escape from the Earth gravitational or any planet's gravitational pull. So it can be your hyperbolic profile, or it can be your, and this can be your, uh, or even your parabolic profile. Okay. So that is how you do the analysis. Okay. Hope this is clear for you, and you can try practicing the exercise of your own. And see you in the next video then. Thank you so much.